Hello everyone, this video is a continuation of a unit on quadratic equations. In this video we will talk about multiplying and factoring quadratic expressions. I want to look at the relationship between these two and then give you one main rule that you can use to factor. Alright, so first of all, the relationship between multiplying and factoring. These are kind of like inverse operations. If you look at an example like 3 times 4 equals 12. We have two things that are multiplied, and then their product is 12. We say that 3 and 4 are the factors of 12. So if we said something like factor 12, then to factor is to find some factors that together multiplied equal that 12. Now we have a variety of ways that we can factor 12. We could also factor it as 3 times 2 times 2. I could factor it as 12 times 1, or 6 times 2. So it's not necessarily clear when we say factor how, which of these answers are we actually looking for. So when we get to algebraic expressions, when we say factor, there's built in the assumption that we're trying to find prime factors. Right. So for 12, we're more interested in something that looks like this, 3 times 2 times 2, and we don't really want all of those options with 4 or 12 or 6 as factors, since those are not primes. Okay. Here are some other examples of algebraic products, and then we can look at their specific factors. All right, so here we have x plus 1 and x plus 3 are the factors of this expression on the right, x squared plus 4x plus 3. Now to see that they're the factors, we need to multiply them and make sure that it does equal the thing on the right. Just like as with 3 times 4, we need to multiply 3 times 4, and if it equals 12, then those are factors of 12. All right? And we would say that 3 times 4 is a factorization. All right, and then this last example, something can have, an algebraic expression can have more than 2 factors. Here we see 3x plus 1 and x plus 3 are all factors that when multiplied equal 3x squared plus 4x plus 3. So a lot of times in these problems you'll see two instructions. You'll see multiply, which means go from the left hand to the right by multiplying. And for this one we could use FOIL and the distributive property. But if the directions say factor, then what we want to do is go backwards and work from this product to try to figure out the things that were multiplied to equal that product. Okay, so let's go the multiplication direction first. Multiply each pair of binomials. Remember, binomials means expressions with 2 terms. So 2x minus 5 is a binomial. Alright, so we can just use FOIL to do this. Multiply 2x times 3x to get 6x squared. Then 2x times negative 8. Then, alright, that's the outers. Then the inners, negative 5 times 3x. And finally, negative 5 times negative 8, which is positive 40. And then it's implied that you should always combine like terms. So we would make this 6x squared minus 31x plus 40. Alright, the second one, 4x times 2x is 8x squared. Then 4x times 5 is 20x. Negative 9 times 2x is negative 18x. And in the last place, negative 9 times 5, negative 45. Combining like terms, we've got 8x squared plus 2x minus 45. Okay, what do we mean by factor? So factoring the expression means to write it as a product of irreducible expressions. And irreducible expressions are kind of like the prime numbers for algebra. All right, so how do we, for prime numbers, we have a list. We know that the primes are 2, 3, 5, 7, etc. And we have a rule to decide if something is prime. We check whether or not its only two factors are 1 and itself. So we need rules for algebra to decide if expressions are irreducible, or what makes an algebraic expression kind of like a prime number. So here are the things that you can check to make sure. You want to make sure that the greatest common factor of all the terms in the expression is a 1. So for example, 3x plus 6 is not completely factored because both of those terms, the 3x and the 6, each have 2 as a factor. And then secondly, we want to use the one factoring rule, and this is the one that I'll give you, to confirm that nothing else can be done. So there's another way to check and make sure that this thing is fully factored. Alright, so let's practice factoring out the greatest common factor. Right? I will show you the long way to do this, and then if you can see right away what it is, or you have another way that you prefer, then just stick with that to factor out the GCF. Okay, so what I like to do is list all of the terms, 3x squared, and then negative 15x. All right. And then next to those, I'm just going to break those down into, first of all, prime numbers. So 3 is already a prime, so I'll list that. Negative 15, I'm going to notice that there's a negative 1, pull that out. And then the prime numbers would be 3 and 5. Right? And then I go back and look at all of the variables, and I want to break those down so that they each have exponents of 1. So x squared, I'm going to write that as x times x. Right? And then 15x, just have a single x. Now I look up and down vertically, and I look for pairs of any factors that match. All right, so negative 1, there's no negative 1 up here, all right, to match with. But the 3, I do see a matching pair of 3's, and then I do see a matching pair of x's. Right? So then I just follow those down, record what the matching things were, and multiply them together, and that gives the greatest common factor. Right? So there's a 3 and an x that can be factored out. Right? Let me show you what this looks like with, put that down. Let me show you what this looks like with regular numbers. Right? And you can confirm you may be a little bit more familiar with those. If I had 12 and 15, then I would break those down into prime numbers. So 12 is 2 times 2 times 3, and 15 is 3 times 5. Circle anything that they have in common, follow it down, and here it's just one thing, so the greatest common factor is 3. All right, remember that what we mean by GCF is the largest number that can divide evenly into both of these two numbers. So it's the same for these algebraic terms. We're looking for the largest term, numbers and variables, that can be evenly divided into each of these two terms. All right, and when we mean evenly divided, notice we're not going to get decimal numbers when we factor it out. Right? And same thing with the variables. I'm not going to get like a piece of an x or something like that. All right, so I'm always going to get, when we factor it out, we'll always get like another x or an x squared, maybe x cubed, but nothing like x to the 1/2. Okay, and then what's left to do is to see what's left when you factor this out. And what I really should have done is left my work showing for finding the GCF. Right, so I've recopied that. That'll be helpful. Right. So this is kind of like using the reverse distributive property. I want to take out a 3x from each of those terms and then see what's left. Right. Well, if I look at just the 3x squared, the circled things are the things that are gone, the 3 and the x. So the only thing that's now left is an x. Right. And when I look at the negative 15x, I've taken out a 3 and an x. So what's left is a negative 1 and a 5. And we multiply those together to get negative 5. Okay. Now we can do a check to make sure that this is the correct answer. And I'm going to check by remultiplying. So if we distribute 3x to each of these terms, we end up with 3x times x is 3x squared, and 3x times negative 5 is negative 15x. Now, if you get your original problem, which we do, okay, those match, then we know that the answer was correct. All right, so that's just the check. But the actual answer, if you're asked to factor out the GCF, is 3x times, in this case, x minus 5. Okay, so that's your answer. Okay, the next one. 4x squared plus 6x. So I'm going to list the terms, and then I'm going to break the numbers down into prime factors. So 4 would be 2 times 2. Right, and then x squared is going to be x times x. And then 6x, 6 becomes 2 times 3, and then I just have an x. Circling the ones that they have in common, I see 2 2's, and I see a pair of x's, and nothing else matches. So multiplying, the greatest common factor is 2x. Okay, so I know this factors as 2x times something, and since the problem is a binomial, it's going to have 2 terms still in the answer. Right. So from the 4x squared, I noticed that what wasn't used in the GCF is 2 times x. And then from the 6x, there was a 3 that was not used, so that's going to be a plus 3, a positive 3. Okay, so that's the answer. And then as a check, I can use the distributive property to remultiply. So do 2x times 2x, which is 4x squared, and then 2x times 3, which is 6x. And that does give the original problem, so this is good. All right. Just a reminder, if we were doing this with numbers, right, if you saw the instructions, factor 12 or something, okay, then you could write that 2 times 2 times 3, and then the check would be remultiplying to see, does that actually equal 12? And yes, it does. We can also factor out the greatest common factor from 3 different factors, right, from a trinomial, 3 different terms. So I will do the same thing. I'll make a list of the terms, negative 5x squared, negative 15x, and positive 20. Okay, then I'm going to list all of the primes and variables. And if there are negatives, then I'm also going to write those. So a negative is going to be negative 1, and then 5 is a prime number, and x squared becomes x times x. Negative 15x becomes negative 1 times 5 times 3, and then we just have an x. And 20 becomes 2 times 2, that's 4, times 5 is 20. Now, when I look for the common factors, I need to look for things that are common to all 3 of these. Right? So even though the first 2 terms share an x, that can't be part of the greatest common factor because it's not a factor of 20. So I'm making a circle of 3 different things, and I can do that with the 5's, but nothing else. Right? So here the greatest common factor would be a 5. And then in parentheses we'll write whatever's left in each of those 3 terms. So for the first term we have negative 1 times x, which is negative x squared. For the next one, it's negative 1 times 3 times x, negative 3x squared. Oh, I'm sorry, just negative 3x, not squared. And then the last term, 2 times 2, is a positive 4. And then that's done. All right, and as a check, try to distribute the 5 to each of these and make sure that it does equal the original problem. Okay, let's try the next one. What do we do if we're finding the greatest common factor of something that's already factored? Well, in this case, I just need to check and make sure that each of these factors is fully factored. So this would be similar to if we had 3 times 4 is 12, and it's similar to noticing that 4 is not a product of prime numbers, so I would break that down further into 3 times 2 times 2. So what I want to do is look at each of these expressions individually, so 4x plus 9, and to make sure that's fully factored, I'll do the same thing. All right, I'm going to line up 4x and 9, break them down into their factors, so 2 times x, and 3 times 3. And I don't see anything that I can circle that they share in common, so that's fully factored. Then I check the same thing for 8x and negative 6. All right, so 8 becomes 2 times 2 times 2, and then times x. 6, we've got a negative 1 times 2 times 3. And here I actually do see something in common, the 2's. So that needs to be factored more. And I can take out the 2. And then in the 8x term, whatever's left is 2 times x, or 4x. All right, and then in the negative 6, we have a negative 1 times 3 left, or minus 3. Right, and then in this expression, I'm just going to carry down or rewrite the 4x plus 9. And then the only other thing we do, if you have kind of a number smushed in the middle here, or some sort of a monomial, then that gets written out front. So we rearrange this and put 2 first, and then 4x plus 9, and then 4x minus 3. Okay, and that's your final answer. Alright, I think we'll stop there, and then I will make another video talking about the single rule that you can use for factoring.